session on advanced milling and classifying technologies. And that's going to be brought to us by Fives. So before we get into that, just for those of you who are new, I'd like to introduce WCA. And WCA is a non-profit company. We have a very sort of democratic approach to life. All of our members, large and small, have the same rights, the same ability to appoint directors and so forth. And we support and encourage the industry to try and move towards full decarbonization. So most of our services are really around sharing best practices. And the webinar today is very much in this vein. But we also have services such as benchmarking and gap analysis and member forums. So member forums are relatively small events which we hold at members' plants to illustrate a particular best practice. And these obviously have been suspended during the COVID virus. And one of the other things that we're kicking off to try to compensate for that suspension is a project we call a Pegasus project, which is performance evaluation gap analysis. So this is a service, if you like, that starts with setting some project objectives around optimizing energy efficiency, maintenance, and so on. And then we have a benchmarking phase, so we collect information and compare and look for opportunities to improve. And then finally, the plant visits. So hopefully this would be after the COVID travel restrictions are lifted, where we would look at the opportunities in more depth at the plants where the improvements were planned. So we've had expressions of interest from members around the world. We still have openings for another 2 or 3 companies within this project. So if it's something that you're interested in, if you're a member, then it's offered at no charge. If you're not a member, then please join first. We expect to kick this off probably in August. So do let me know if you're interested. So I'd like to move to today's topic, and today's topic, as I mentioned, is on milling and classifying. And today we have Fives presenting this to us. So Fives is a global company, as you can see from this graphic. They have business all around the world, from more than 100 sites and 8,000 or so employees. And Fives have been, I think, a very interesting company in that if I compare Fives with other equipment companies, there are some things that stand out in my mind. One of them is, of course, that they developed and patented the HORROR, the horizontal roller mill. So they have equipment offering that is different from other suppliers. But I think another thing that stands out for me, and I used to, before the cement industry, I used to work in industrial minerals, so perhaps this is one of the reasons that it rings a bell with me, is their classification technology and their emphasis on classification and the importance of classification in terms of the efficiency of the mill. I think the third thing that also goes along with that is that partly because of classification, partly because of other factors, they have a clear focus on the product quality and the opportunities for improving or redesigning products as a result of milling and classifying. Anyway, I'll quickly get out of my technical depth if I'm not careful. So I'd like to hand over the floor, if you like, to Olivier van Lerenberger, who's going to further introduce Fives and introduce his team for today. So Olivier, let me stop sharing here and I'll hand over to you. Thank you.
Right, thank you, Ian, for the introduction, and thank you for giving us the opportunity today to introduce Fives solution to your members and to others. in the fields of grinding and classifying. As a World Cement Association associate corporate member, it is a great honor for us to hold this webinar and share with you our experiences. We will roll on a presentation into two parts. First one will be on grinding with a focus on our FCB Euromill grinding system. And thereafter we'll go to classifying and drying solution with a focus on the FCB TSV classifier and other solution. For this purpose, I will let my colleagues roll out the presentation. Mr. Didier Bourbon, who is Asia Sales in Charge, and Mr. Eric Ede and Philippe Niel, who are the product managers within Fives FCB. They will thereafter handle the Q&A session. Thank you for your attention. Didier, your turn.
Hello, everybody, and we are pleased, despite the COVID, as you see, we have to wear protective masks because this is a present regulation in France. So we are pleased to be able to share with you some hints on our technology, whether it's grinding and or classifying and drying. We actually split this in two because we feel that at the moment, obviously, the really brand new projects are probably a little bit complicated for everybody in the industry due to the CapEx restrictions. So we also will present some results, some process results resulting from upgrades, which are coming at much cheaper budgets and are therefore more feasible maybe in the short term. So I will hand over to my two colleagues and I will now share my screen to start the presentation. Enjoy it, all of you, and feel free to ask questions. After the presentation, we will have a Q&A session where we will be pleased to answer your queries. Thank you very much again, and let's start this.
Non, ça passe la suivante. La caméra est allumée. La caméra est active.
Non, c'est parce que tu as appuyé sur le clic.
On passe les slides.
Avec le clic.
Hello, everybody. I'm Eric Ede, Euromill Product Manager by Fives FCB. Welcome to all participants for this webinar. I'm very pleased to participate and will introduce you our FCB Euromill grinding plant. First, I will not go into the detail of the technology of the machine, and I will invite you to have a look on an existing video on our website that will describe you more in detail the technology of the machine, its parts, and so on. It's not the main subject of this webinar. We would like to talk about the grinding plant itself. Euromill, as other mills, as classical mills, work in closed circuit on a TSV classifier, resulting in two things. First, very compact workshops. I will discuss a little bit more after, and distinct functions, and indeed 3 distinct functions: grinding, drying, and classifying. On this flow sheet in closed circuit, as said before, we can see these 3 distinct functions. Many flow sheets exist, always in closed circuit with more or less complicated, let's say, configuration. This one with the so-called aero decanter is the most flexible one. allowing to deal with very moist material and also with fine material. We see on this flow sheet the three functions. The green one, the grinding function that is basically ensured by the oro mill itself. The classifying function, ensured by the TSV classifier, and the drying function, ensured by the so-called aerodecanter. This aerodecanter permits to deal with moist material and also fine material, as said before. So this is a perfect layout for separate grinding centers, modular plants, and also it permits to work with ultrafine products. To go a little bit more in detail in the operation of the aerodecanter, let's have a look on this slide. On the left part, we have a reminder of the previous flow sheet. How does it work? The material is fed, the mill outlet material, the material that has already been grinded, and the feed, the wet feed, are fed in the hot gases column rising up between the aerodecanter and the TSV classifier. At this point, the coarsest particles are falling down into the aerodecanter, a bit dried, and then are conveyed back to the mill for grinding action. The other particles are conveyed by the hot gases into the classifier. Hot gases, these particles are dried. Classifier, these particles are then classified. The finest ones are recovered either in bag filters, this is the case for cement, or into cyclones, this is the case for raw mix. The coarsest one, the rejects of the classifier, are conveyed back to the mill for grinding action, building the circulating load of this closed circuit. On the right side, you can see two application examples. The first one is for raw mill grinding, an existing plant in Mexico that permits to deal with aerodecanter, a feed moisture up to 6.5% of raw mix. On the very right side of this slide is a picture of a Teresa plant in the Philippines. It's a cement grinding plant that permits to produce cement with up to roughly 30% of pozzolan, but this pozzolan is very moist with about 25% moisture, and this pozzolan is handled and dried into the aerodecanter. Let's have a look on some picture of existing installations. You can see on the left and right parts of the aerodecanter sketch some pictures of aerodecanters installed in the Philippines and in Mexico. In the Philippines, it's Teresa plant. In Mexico, it's a recent Tula plant of Cementos Fortaleza. You see some details of the aerodecanter. And on the very right side of this slide is a picture of an existing plant in Texas, in United States of America, using raw grinding. So, as you have seen, a raw mill can be used, thanks to its flexibility, for raw mill grinding or for cement grinding, but also can be used in mineral industry. On the pie chart, you can see the global distribution of existing plants. Roughly 60% of our references are for cement grinding, 20% for raw mix grinding, and the rest, roughly 20% as well, in slag and mineral grindings. This flexibility is also due to the fact it is an identical machine. It is exactly the same machine that is used for raw mill grinding, for cement grinding, or mineral grinding. So, identical machine can be used for the two applications in cement plants, for raw mill grinding and for cement grinding. We have here a list of references of existing plants with 1 or 2 lines that are equipped with a raw mill for both raw mix and cement grinding. The plant of Marinil in the United States of America, plant of Tula, Pazapan, Cerritos, Tepetzingo in Mexico. The advantage is obvious, the same operation, but not only, because since these are identical machines, these are the same spare parts, the same maintenance routines. A raw mill allows a large energy saving. For sure, it's one of its advantages. Large energy saving compared with ball mill. We have here some examples of energy savings for different type of cements. Same freebie, it's a high slag content cement with 70% slag. Same one, it's ordinary Portland cement, let's say clinker and gypsum, basically. And same to AP, pozzolanic cement with roughly 20% of pozzolanic. The saving range is in between 30 to 50%, rounded values. The difference can be explained either by the grindability of the mix or the fineness that has to be reached. The main gap here, the major saving, is here due to the fact the efficiency of grinding bed, compression grinding is more efficient than ball mill grinding. And you see that the most of saving are due to the fact the specific energy of the mill only is much lower for raw mill compared to ball mill. But we have also significant saving compared with vertical mill. For sure, they are lower, but you can see on this picture 2 comparisons for raw mill grinding and cement grinding, and the range of saving is in between 20 to 25%. I will comment a little bit later on, but there are on this slide for the same cement 2 targets, either in terms of strength target or blade target, because one of the advantage of the raw mill, we will see a little bit later, is that the cement quality can be reached at lower blade compared to ball mill or even vertical mill. I mean, same strength development are reached at lower blade with raw mill. Last, to finish the comparison, 2 figures to compare the energy savings in cement grinding, raw mill versus the coupled ball mill plus roller press. The saving is roughly 30%, 28% in case of Portland cement, 30% is in case of pozzolanic cement. To stop to compare with other technologies, here is are given some figures of industrial results of raw mill plants. I will not read all these values with you. You will have time to do. Just comment some of them. Just for your understanding, the blue values are values that have been obtained during PGT test, performance guarantee test. So these are performance test value, performance that has been industrially achieved and validated. And I have highlighted on this slide two couples of values. In the top, these are raw meal references. The plant of Tula in Mexico and the plant of Barroso in Brazil, one of the biggest raw mill installed for the time being, 4.4 meter, with a specific grinding energy of the plant that is below 11 kilowatt hour per ton, full grinding plant. And in the bottom, the references and the figures of two Philippine plants, the one of Teresa and the one of Nosagaray, producing cement with a very high CK ratio. Cement and clinker ratio means having a lot of additive in the cement. This is the pozzolanic cement I mentioned before, that can be obtained thanks to the aerodecanter with a specific grinding energy, let's say in between 25 to 26 kilowatt hour per ton for 1.8 CK ratio. To come back to my first comment, the capacity of the installation, here are some typical dimensions of plants, giving the height, the width, and the length of the footprint of this plant. Here in the case of raw mix grinding, note that the raw mill grinding equipment installation can be structurally combined with the Praetor tower to even reduce the footprint and obtain an even more compact arrangement. This has been done in Texas, for example. Our mill is also, for sure, a compact installation in case of cement grinding. And here are given typical lengths, widths, and height of cement grinding plant for our mill, for cement grinding, sorry. The flexibility of the Oro mill permits also to obtain not only a wide range of different cement, but a very stable and interesting quality of cement. Let's compare here some interesting figures of quality results, comparing the cement from Oro mill, I will name it Oro mill cement, compared to the cement obtained thanks to ball mill plants. I will call it ball mill cement. So it's interesting to note and to keep in mind that all the quality parameters are met for commercial name of cement, for example, for SEM1, for 1P, for OPC, whatever the country. So we reach the quality target, we obtain the same water demand, there is no particular problem in terms of flowability, in terms of workability of cement or concrete mortar. But fact is interesting to note that the same quality is obtained with a cement, Oro mill cement, but has a lower blend than a ball mill cement. Typically, there is a difference of roughly 300 blend. So to summarize, the same quality of cement is reached with Oro mill with about 300 blend less compared to ball mill. Just note the values here are not only a small test value, but are average values from statistics over 1 year of production, so it's representative. To have some more example of cement quality, we can here have recent industrial results. In the middle, the plant of Tula is an existing grinding plant in Mexico, having both technologies, ore mill from FCB with aerodecanter and ball mill from FCB with a TSV classifier. So we had the opportunity to compare the two technologies for the same cement. And we confirm here, as you can see on these figures, that we obtain the same quality of cement, for sure with a significant saving in energy, with a lower blend, exactly 300 blend lower, just to confirm what has been said before with another reference. On the right side, you just have for information some quality results of high resistance cement or European cement with 52.5 megapascal strength at 28 days. And to the left side, this well-known now Philippine plants of Norzagaia and Teresa with high CK ratios. The comparison can also be done in terms of quality with a vertical roller mill. And in this typical case, the observation is similar to the one we can do with a ball mill. I will not come back to the savings in terms of specific energy that are here in this case between 10 to 15%. But it's also important to note that the quality in terms of strength development, it means the quality of the cement that cement manufacturers sell, is reached and obtained with lower blend for ore mill compared to vertical roller mill. The stability of the quality is ensured by the stability of the operation. The stability of the operation is a very important point for ore mill. The mill behavior is stable and controlled. On automation point of view, the behavior of the plant is predictable. So it is easy to have an automatic operation of this plant from startup to stop. There is one push button for the operator to start the plant and the same button to stop the plant. There also exist some recipe tables. These recipe tables are indeed a list of parameters that are automatically validated at selection. It means when the operator starts the plant, he also chooses the quality of its product on all parameters from the composition, means the percentage of each component, the speed of the classifier, the grinding pressure, to the silo destination are automatically selected. There are for this stability three main regulation loops. The first one is one for the glass flow, a very classical regulation loop that permits to have a constant flow through the classifier, ensuring a constant stability of the final product quality. Loop that can be divided in two parts for temperature and pressure regulation, very classical one. And maybe the most important one, circulating load regulation loop that permits to control the material flow through the mill, ensuring its stability. I'll show you on this slide some key figures that are, according to me, self-explanatory to show the availability and the reliability of the oral mill grinding plant. We have, for example, some cases more than 7,600 hours of operation per year in the plant for cement mills, even more than 6,200 hours of operation in case of raw mill grinding. The average availability is around 95% availability of the whole plant. Combined to a long lifetime of the wear part, of the spare parts, that permits to reduce maintenance needs and reduce maintenance costs and so on. We have more than 50,000 hours of operation for the shell liner, for instance. And the shell itself can last more than 20,000 hours of operation, typically between 20 to 40,000 hours of operation, depending on the abrasiveness of the product, on the maintenance need. Just to have a quick view on the repartition of the oral mill plants over the world, there are 27 plants in the Americas, 21 in Asia, and 16 in Europe, dealing mostly with cement and raw grinding and slag grinding. The complete list is available on our website. This last slide is a summary of the advantages and benefits that has been mentioned before. I will not read all of them, but already said, higher cement quality with less blend, very flexible machine, high energy efficiency, low electrical consumption are advantages of this grinding plant. So I finish here. I hope you have enjoyed this short presentation. I'm waiting for your question. I let now talk my colleagues, Philippe Niel.
Thank you, Eric. I'm Philippe Niel, Grinding Products Manager in Fives FCB company. I will give you a short but as complete as possible overview of the equipment developed and proposed by FCB in the area of separation and grinding plants. First, regarding TSV classifier, this classifier called TSV was developed in the end of the 80s. It belongs to the family of the third generation dynamic separator, which are many now. The size which are available start from 1 meter to 8 meter diameter. In fact, the smaller one is installed in our research center with only 400 diameter. The biggest one that we install is in Qatar. It's a 7,500 meter diameter in raw mill plant. TSV is, of course, applied in the three grinding plants in the cement industry. It means in raw mix plant, in raw mix grinding plant, in solid fluid grinding plant, and cement grinding plant. Mainly, TSV references are in cement industry, but we have also references in mineral application, like for carbonates, phosphates, silicium, manganese oxide, and others. Also, some reference in our sister company, Fives FCB, in the field of anode pass preparation with calcined petcock in alumina plant. The geometry of the classifier, the height of the classifier depends, in fact, of the range of fineness which are the targets. And we start from the TBF, what we call the TBF, the very low fineness, with cut size between 90 to 500 microns, down to the ultra high fineness from 3 to 30 microns cut size. You have the split of the different size, different types on the left here. The main portion comes with HF TSV, which are in cement grinding plants. Here is what you probably know. It's the trunk curve with the different shapes of trunk curves achieved with dynamic separator, starting from first generation separator with here high bypass, nearly 50%, and very smooth slope of the selection curve. If we look at the green one, the bypass comes down to 0%. Of course, not in all the conditions, but in condition with low specific load and not too fine fineness, 0 is achievable value. So there is 3 results with the third generation separator TSV. First, low bypass, as you can see. The steep slope between, which is, for example, between 225 to 275, steep slope of selection curve, which enable a precise adjustment of product fineness in operation. And this steep slope is mainly due to our original shape of turbine blades, which are shown on the left here, with different higher lengths between blades L2, bigger than L1 at the outer part of the turbine. This is a patented turbine shape, turbine blade shape. The third effect of the high efficiency separator is a strong reduction of coarse particles, which gives for cement better compressive strength, or for raw mill better burnability, and the same also for solid fuel. Now I will share you some upgrading experience starting from third generation separator to our TSV. Here, the example comes from Poland. We start with the existing plant with third generation separator with 7.1 diameter. And we install a TSV 3.2 diameter only. If you look at the total power installed before, it was 310 kilowatts, and after revamping, we installed 450 kilowatts. So it means 140 kilowatts more and this installed power, therefore, hardly changes, while the revamping will allow a production gain of more than 20%. Installed power of TSV is lower than classifier of competitors. This is due or thanks to the vortex breaker plates in the inner part of the turbine, which is also a patented item from FCB. if we talk about the arrangement with this TSV 3.2 diameter, in fact, the existing separator has cleared enough space to install a new back filter and fan. So it was quite easy to install the new equipment, new filter and fan. Staying in this plant in Poland, Chelm, this is an example of what was the capacity increase by installing the TSV. In fact, guaranteed outputs were calculated based on our FCB index grindability test, and with these two figures, first at 3,700 blend, capacity increase, guarantee increase was 97 ton per hour instead of 80 ton before. It means capacity increase by 21%. Same ratio was applied for a new type of cement, which was not produced before by the client. We start from assume so the guarantee was 67 ton per hour with 21 capacity increase guaranteed, and we reached during performance test 70.9 ton per hour, meaning 28 calculated capacity increase. Mill specific power consumption was decreasing in the same way, but up to 30%. Again, in this plant, with another production, here it's OPC cement, same one. You can see what was the performance, the trunk curves that we achieved during the performance test. We sample collecting during the performance test. The cut size here is quite low, about 20 microns, corresponding to this high quality cement, same one at 4,500 blend. And you can see this, the figure obtained regarding acuity or sharpness index. The ratio between 225 and 275 is 0.59, when common value for this type of separator can be between 0.3 or 0.35. The bypass here achieved is 8%, with the good result in regards with low cut size. Five years later, the performance of the reliability of the performance and reliability of the TSV led the customer to repeat order for 2 other mills with the same TSV. Here here is a panel of capacity increase with the same scenario. I mean, starting from conversion from first generation dynamic separator to TSV classifier. For example, for constant strength, which is the end goal of, in fact, of the customer, it's the quality of cement. The capacity increase is between, with these two examples, 26 or 57%. Just here, an illustration of what are the Rosen-Ramler slopes obtained with this separator, TSV. The consequence of the high sharpness of the selection is materialized with the high slope of grain size analysis diagram. The slope as bigger as 1.47 for the same one in Chelm is obtained is reached up to 1.37. What is not shown in this diagram, in fact, it's there is a break in the grain size slope of finished products around the D50 or cut size of the partition curve. This slope rupture is all the marks when the circulating charge ratio is high, with clearly a visible effect of the separation. Again, regarding quality of cement, due to the high sharpness of the selection and the relevant reduction of coarse particles, if you can see here with this cement, CM2AS, with 15% of slag, residue at 32 microns was before the upgrading 11.5. And it goes down to 4.9, yeah. And when reaching the same resistance at the end. In fact, at the end, the customer set new targets, R32 between 6 to 7, yeah, in order to keep the same and fulfilling, in fact, the quality requirements of the client. It means 62 tons per hour were able, client was able to produce 62 tons per hour instead of 49 before. Sorry. Plus 27% capacity. Here are shown the different configuration of TSV with the different feeds, for example, starting here on the left from top and bottom feed inlet with quite classical arrangement in cement plants. The blue one, dark blue one, is corresponding to the coal separator with bottom feed. And the two other are with air volute inlets. And the last one on the right is in vertical mill for coal mill. So now I will continue with the drying application in grinding plants. I will present you some solution here. The purpose of the system is to split the drying of the raw material between the mill itself and a duct called flash dryer, which is a bypass duct outside of the mill. This system assumes that part of the material feed is fine enough to be blown up in the gas entering the flash box. This fine fraction is also most often the wettest fraction, which gives to the system its relevance and efficiency. By splitting the drying of material between the mill and the bypass duct, we limit the needed hot gases entering the mill, and we therefore limit the gas speed in the mill, as well as the resulting pressure losses of the mill. In doing so, there is no over-ventilation of the mill and grinding condition remains optimal. One example, recent example, is in Qatar or in raw mill plant, 450 tons per hour. Mill is 5.6 diameter, installed power 6,600 kilowatt. And you can see in the first floors the invert V, which is the flash duct. Process result, as I told you, is 450 kilowatt, 50 ton per hour at 8% moisture, with only 26 millibar for pressure drop of the mill. This is an overview of, in fact, of all the drying solution with ball mills, starting from a basic ball mill without any equipment, without any dedicated equipment for the drying. The first step is to add the drying chamber in the shell of the ball mill, and then we install this inlet mill flash dryer that I show you, and doing so, we are able to reach to dry up to 8% moisture at the mill inlet. The other system proposed by FCB, it's quite more common example. It's FCB flash dryer with a venturi shape of the duct. This is applied for fine or granular product up to 10 millimeter diameter, such as fly ash, bottom ash, pozzolana, slags, or minerals. In separate grinding plant or associated with mill, it is installed below TSV. It has a low investment cost because it's a static equipment with a low footprint. The results are a reduction of overgrinding of fines which are already at the correct fineness. It's the first selection of fine product before to come in the mill. It decreases the specific electrical power with a low pressure drop of the mill. And it decreases also the mill internal wear due to lower moisture in the mill. This is an example of flash dryer in Sashi testing in Italy. A picture on the left, which shows the three hot gases sources, hot gas generator, hot air coming from clinker cooler, and hot gases coming from the preheater. The purpose of this project was to dry fly ash coming from outdoor storage of thermal power plants. There was a huge waste reserves waiting for valorization. Before the project, the quantity of fly ash was limited due to the drying impact. After the installation of this flash venturi and TSV, we achieve the following process result with more than 40% capacity increase, starting from 85 and up to 120 tons per hour. This is a short list of flash dryer application for fly ash. And last slide is a summary of what I said before. In fact, if you want to summarize it, it's that thanks to the wide and available range of FCB equipment, FCB can offer proven solution, guaranteeing the best efficiency and highest capacities. The separation of the drying, grinding, and selection function is in the relevant equipment, B-mill, or mill, flash dryer, TSV, allow the best efficiency in new workshop or modernization of existing facilities, with opportunities for cement with industrial byproducts or waste. From this point of view, as Eric showed you, the mill workshop with ADC and TSV constitute the most relevant achievements applying this principle of separation of function, optimizing performance, increasing drying possibility without significant impact on the investment or OPEX, except, of course, for the inevitable power consumption to dry. Thank you for listening. Now it's time for Q&A session.
Okay, so thank you very much, Eric and Philippe, for your presentations. We already have a number of questions coming in. So can I just ask everybody, if you want to ask questions, please use the Q&A function and not the chat. We have some questions on the chat, which we will get to, but it's easier for us if you use the Q&A function, because there's a kind of system in there where we can tick off the ones that have been answered. So before we go to the questions, I'd just like to do a couple of polls. So the first one, I'd like to ask all of you as participants a question about where you are in terms of grinding technology. So Manon, can we have the first poll? So what type of cement mill do you have in your plant? So if you've got many plants, then please answer this for the most recent plants, the most up-to-date plant. So what do you have? Ball mill, vertical mill, roller press, horizontal roller mill, so a horror mill, or perhaps you're not a cement company. So I just give you a few minutes to answer, a few seconds rather, to answer that question. Okay, so good opportunity for you, Didier and Olivier. So we have nobody currently using horizontal mill. So most of you have moved away from a basic ball mill to either vertical mill or roller press plus ball mill. Okay, so maybe that's interesting when you think about the answers to the questions in terms of that comparison. And then we always like to ask a question as to whether you found the length of the presentation to be about right, or too long, or too short. So if I can give you a few seconds for this one too. Okay, excellent. So 93% said just right. So congratulations to Steve on that result. So if I could invite all of you, Didier, Olivier, Eric, and Philippe, to switch on your videos and microphones, then we'll get to the questions.
Okay, can you?
So I think some of these you've answered during the presentation. So perhaps we can run down these, and if they're already answered, then we'll skip over them. When we've done the Q&A ones, we'll just go to the chat and pick up the questions that were asked in the chat as well.
Okay.
So I mean, let's take it from the top with a question from Philippe Laveche de Beau. How can you compare the civil works for the horror mill versus a ball mill and VRM? In terms of, I guess, the quantity of civil works, the capex, and ROI. Gosh, you must love that question.
Okay, so actually, as you have seen, one of the key features is that the workshop is very compact. So actually, the civil work cost is normally less than what you have for ball mill or vertical roller mill, and even the difference is bigger when you have a roller press combination, because the roller press combination has to house even more equipment inside the same building. One point that can be said also is that therefore it was a key issue when we won the project in the Philippines with Lafarge, now CRH plant, because it was a greyfield project and we had to fit in a very narrow space. So not only the civil cost, but also the fitting in a limited space was a key issue. So generally, I would say it's more compact, and its complexity from a technological point of view is similar to what you have with a vertical mill, but size and quantity of concrete and so on is smaller.
Okay.
Okay, regarding capex and ROI, obviously this is a little bit more complicated to answer because you have a lot of different factors going in. For example, depending on the countries, either you can use steel construction or concrete because the relative cost of these solutions is quite different depending mostly on labor cost. So we have what we can say is that we have solution on both. Because Fives FCB has its own civil department, and we are able to design and to accompany our customers in the design of different solutions.
Just on that, Didier, is there an application for which the horror mill has a greater advantage over other mills when you consider it from an ROI standpoint rather than a technical standpoint? Is it easier to use an ROI on a raw mill or a cement mill?
But typically, raw mill is interesting because you obviously produce typically 1.5 to 1.6 times more raw mill than cement. So the kilowatt hour per ton advantage is leveraged by a higher production. Generally, what we see in the investment ROI is that the balance is quite the same between raw mill and cement. The combination of drying can be a key asset because, for example, you can substitute wet additives easily. And by increasing the CK ratio, also your total production cost goes down, whereas your production goes up. Because typically the additives are easier to grind than clinker. So not only you dry them, but the production of the mill also goes up.
Yeah, we can add that in addition to what Didier said, that with the system, the Euromill system, we can maximize the proportion of additives. Couple of percent, between 2 to 5% upon application, but this is enabling a better ROI at the end of the day for cement where you have a lot of additives and especially wet additives.
So when you say additives, Olivier, you're really talking cementitious, right?
Yes.
You're not talking about grinding aids or something like this, yeah?
No.
Cement recipe.
Right. Okay, good. Another question from Philippe. He asks whether in your data, your comparisons, are you comparing a horror mill, when you compare horror mill with ball mill, or I guess it applies to other comparisons, is it using the same separator or is each using their own separator?
Actually, in our technology, we use the same separator for both ball mill and horror mill, but with some, let's say, different design and sizing features, but it's the same basically. So when we compare, in general comparison, we compare always with third generation separator. That means more or less state of the art and not old ones, because old ones would not be relevant.
Okay, so your comparisons with ball mills are sort of fair, are really a comparison of the mills.
Yes.
Not a comparison.
Otherwise, it would be biased because the efficiency of the ball mill would be artificially lower.
Right. Okay, good. And then a question from Artem Kozinets. Good morning, Artem. What is the typical specific air load for a TSV separator? Yeah, I guess, is that one for you, Philippe?
Yes.
I think so, yeah.
For inlet, the specific load in a ball mill is 2.3 kilo per cubic meter maximum. Outlet is 0.8.
Okay, great. And another question from Artem. Artem, I'm not sure if you're deliberately winding us up here, but anyway, what is the reliability and MTBF level for the horror mill compared to a ball mill or VRM? The reason I say this is, you know, obviously there are a lot of things that go into MTBF, and the reliability of the mill is just one factor. You know, if you've got problems in the process, clearly you're going to have downtime regardless of what the mill is. But how do you look at that in terms of just reliability? How do you compare the mills?
Okay, Eric will answer that one because he's not only product manager, but he's also in charge of following the park of existing machines.
Okay.
So mean time between failure is generally a key indicator we don't consider a lot, but this is our mill plants are reliable, and I would say that generally speaking, there is no hopefully no incident during operation. Typically, a mill can operate. It depends on the way you will calculate it, but a mill can operate during three days of production if there is no need of stoppage. Regarding the mean time between failure, there is no issue, but I have no figure to show to compare.
Yeah, I mean, in my experience, mean time between failure is very much a management issue.
Yes, yeah, we would agree to that.
Tremendous improvements in MTBF without making any changes in equipment in plants when you have new management that is better able to, you know, to manage the maintenance and so forth of the plant. So I think that's a bit of a difficult question to answer, Artem. But
yeah, we can add, Ian, if I may, we can add that we've got a client having a wide install basis of Oromill, so he's able to share in various plants the operation with the same mill, same system. And the reliability that he is mentioning to us is about 98%.
Okay. So let's move on to the next question. I think, sorry, the next one is water demand. I think you covered that in the presentation. So Artem also asks, what's the typical maintenance cost in terms of wear parts, labor, spare parts for a horror mill, either in euro per ton of cement or raw meal? Do you have those kind of figures?
Yeah,
I think it's a
an
difficult
example I have in mind is
things going in there.
Yeah, an example of I have in mind is in the range of around 4.5 euro per ton in Mexico. So that basically includes parts, labors, and let's say wear parts, spare parts, and labor. It's an average on several years of operation in Mexico that I have in mind because it was given to us by the plant manager when we visited the plant.
But is that just the mill, Didier? Is that the whole
No,
plant?
actually they calculate this per workshop. Not not only mill. So it's total workshop, because the way they are doing this, which in my opinion is a quite logical way, is to have this kind of figures for each main function of the plant.
Okay.
And they have this, so this concern actually, it's the mill, the elevators, the classifier, the fan, the filters, everything which is in the grinding department.
So I think that must be the cement grinding then, is that right?
Yeah, it's cement grinding.
Yeah.
It's generally a little bit lower for raw mix grinding, because obviously you don't have the filter, and raw mix is more a specific case, because raw mix, the abrasivity can be quite different depending on the plants, especially when you have a lot of free silica in the raw mill.
So we used to compare maintenance costs around the world, and we had a standard within Holcim, which if I remember was about $8 a ton of cement total total cost. But it varied a lot. I mean, in China we used to have maintenance costs which was around $2 per ton.
Yes.
So I think there's a lot of geographical variability.
Yeah, this which makes it difficult to compare is that basically labor cost is quite different.
Yeah. Yeah.
And also recently there have been a trend in many plants to outsource the labor for the maintenance, which means that the way it is accounted is probably not exactly same in the different ways of thinking.
Okay, if we move on to the next question from Philippe. He asks, what's the maximum size you can make one of the modular horror mills?
So the modular horror mill is, we didn't touch it in the presentation because we wanted to present more production result and so on, is a concept that is okay, let's say, depending on the type of cement, probably between 50 and 60 tons per hour. So this corresponds to around 2.8, 3 meter size mill. Above that, the advantage of modularity could be there, but in most cases, probably not, because the pre-assembly will be limited by the size of the mill.
Okay. Just moving down the questions here. Artem asks, what is a typical underpressure before the fan?
Which application?
Eric will, for cement. Let's do it for cement.
Minus 50?
Around minus 50 millibar before fan for a typical cement application.
Okay.
You don't see it on the floor.
And Philippe is asking, what's the average delivery time for critical spare parts?
So generally, what are critical spare parts is always a matter of discussion, but generally we try to have a short lead time, because for most of the size of the mill, we have some critical spares available in our storage, which means they can be shipped quite easily. So obviously, when we have a project, depending on the country, we try also to have some time local, not far in the area, not far from the location of the plants, in order to shorten the delivery time.
And so for the horror mill, presumably the grinding surfaces can be rebuilt, can they? Like
Yes.
you also do a vertical mill, yeah?
Actually, there are basically two grinding surfaces. One is the shell liners. Shell liners have a lifetime in excess of 50,000 hours. So means that, they are not very prone to accidents, I would say. So there is no reason to have early replacement. So this is something which can be planned easily, because it's basically the same style of replacement than replacing liners in a ball mill. They are less liners. So for that one is not an issue. The other part is the sleeve of the roller, and the sleeve of the roller is rebuilt by rewelding several time before changing. So actually, in plants with only 1 mill, generally they do a complete changing. They take out the roller and exchange the sleeve. In plant with several mills, most of the time, and it's the case, for example, in Mexico and others, they have one shaft available for 2 or 3 mills, and the shaft is ready. So you only exchange the shaft, which is an operation lasting, let's say, 3-4 days, instead of having also to replace the sleeve.
Yeah.
So,
we can add that we have also developed a machine that is doing the automatic rewelding of the sleeve. So especially for very abrasive application. And maybe it was not that clear into the presentation, but thanks to the zero water consumption of the process in the mill, the wear is very low. And actually, the wear within the Euro mill is 3 to 5 times less than a vertical mill.
Oh, okay.
So it's less than 1 gram per ton, roughly. It's 0.5 to 1 gram.
You could go for several years then before you have to replace the roller. Is that right?
We do a regular rewelding, and after the lasting is quite extensive. Yes.
Yeah. Today we say 20 to 40,000 hours, which is already several years, with refreshing in between by rewelding. But we have 1 or 2 units of the latest design which have exceeded 50,000.
Okay. Okay, and another question from Artem about the control logic. So do you have a special control logic for roll pressure and the hydraulic system as you do in roller presses?
Okay, so I suppose Artem is meaning the logic to anti-skew, which is used for roller press in case you have an angle which appears between the 2 rollers. So we don't need this for the Euro mill because actually the roller system is mounted on swivel bearings, and the roller is not really parallel to the liners because obviously in the inlet side there is more coarse material than at the outlet side, so it's not exactly parallel. So we apply the same pressure on both sides, and the swivel system will allow self-alignment of the system on the material bed.
Okay. We have 3 questions here from an anonymous attendee. Perhaps we can take them together. The first is the maximum size of the mill feed. The second is the maximum drying capacity with and without hot gases. And the third is, can you use the horror mill for coal grinding?
So first, max side of the mill feed.
It will depend for sure of the size of the mill, but typically for a 3.8 meter raw mill, for example, the max size will be 100 millimeter, something like this. It's not an issue to have some blocks. But for sure. 20 centimeter blocks are a little bit disadvantages, but let's say the 80 around 80 millimeter is not an issue.
But does it affect the grinding power required if you have
No. The big blocks will maybe give some issue with. I don't go in detail into the technology, but can be a trouble, for example, with what we call the scrapers. You have to look on the video to understand how it works, but there is a scraping bar inside the mill. If this bar face big blocks, it can lead to troubles. But the things we have to avoid in this mill, it's like vertical mill, is metallic pollution. But a big block, a stone, is not an issue.
But so with the ball mill system, you know, it's worth spending more money on explosives to reduce the power costs on the ball mill. Would that logic not apply if you were using a horror mill for the raw mill?
No more than for a vertical mill, no.
Right, okay.
To have a certain amount of big lumps, we are talking mostly obviously about raw mix because clinker size is less, is typically less. So it's not a real problem.
Right, okay.
So last one is the next one is the max drying capacity with and without hot gases. So, okay, what we can say is with hot gas, we are able to go around up to 20% water. And we have experience, 20% is a sizing theoretical figure. We have experience up to around 15% for pure slag, because slag, as you know, is often cooled down with water. So it's saturated with water, and you can have 13, 15%, so it's not a problem. Typically, without hot gas, it's in the range of 3 to 4%.
Okay.
So question, can we for coal grinding? So we have an issue for that because it's not a process issue, it's a construction issue, because the ore mill is not built as explosion-proof unit. So because especially on the side of the rollers, you have sliding windows for the motion of the arms and the pressure system, which are not totally airtight. So it cannot be considered as ATEX machine. It is, so we have done process tests on petroleum coke, and it was working. Process-wise, it works, but the mill is not designed to be explosion-proof.
Okay. So we're getting towards the end. Let me just switch over to the questions that were asked on the chat, because some people have been waiting very patiently here. Some of these I think you probably have touched on, so maybe we rush through them quickly if you think we've already covered them. So there's a question here from Yash Srivastava. What is the maximum moisture handling capability of the horror mill without external source of heat?
Yeah, so we just covered it. Basically, we say around 3%.
3%, right? Yeah.
Would be the range.
And there's a question here, another question from Yash. What is the typical particle size distribution of the final product, as in terms of the residue on 45 micron sieve fines for a normal OPC of 52.5 MPa? Yeah, so I think this is going to, yeah. Maybe we can make a slightly more general question here. If you take an OPC with a particular blane, you know, let's say it's, I don't know, 4,000 blane, would the residue be different with a horror mill and a ball mill?
Yes, yes. The residue in particular in this, let's say, coarse part of the particle size distribution, let's say in between 20 and 50 micron, there will be the huge difference. You will have the same, let's say, the same fine distribution, but that gives a blane, so the same blane, but we will have coarsest particles in cement resulting from ball mill.
Right.
Okay. Typically, we can have for OPC produced with horror mill and TSV classifier, let's say peanuts 0 at 45 micron, and have till 2 or 3% at 40 or 45 micron with ball mill. It will depend for sure on the efficiency of the classifier. And so 45 is not, in this case, not very relevant. Use the 32 micron as a mesh, something more representative of the product.
Generally speaking, the PSD shows that we have less coarse particles. And as we know that the coarse particle, let's say above 30, 35 micron, are not so much participating in the hydration. This is one of the key reasons to explain the difference in strength with lower blane, or at same blane, higher strength.
A question here from Vijay Bongiwa. What's the suitable model of your mill for 3.5 lakhs per year of cement? I think that's 350,000, isn't it? 350,000 tons a year of cement. What would be a suitable?
Which kind of cement is it?
Sorry?
For which kind of cement?
It doesn't say, but this is in India, so I guess it's probably going to be blended, isn't it?
1, 2, 3, divisé par, on va dire 6,000. Ça fait 60 tonnes, c'est un Typically, depending on the type of cement, it would be a 3.4 or 3.6 size mill.
Okay.
So, which is a little bit smaller than the most common one. Obviously, it depends on because for blended cement, you generally have a slightly higher capacity, maybe 10% more compared to OPC. So it depends. And in India, generally, it's blended cement because they can use limestone and fly ash, which is generally available in most of the regions.
Okay. So we have just a little time left, so I just probably get to the last one or two questions here. If your question has not been answered, then do contact us, and we'll put you in touch with Didier and his team, and they can answer the question. There's a question here from Kiranmai Sanagavarapu. What is the key factor to look for or to look at when using the same machine for raw and cement grinding? Are the grinding pressures significantly different, and should we do something at the plant when switching between these products? I don't think you're talking about switching between products, are you? You're talking about two different mills, one for raw and one for cement.
Yes.
No, there are generally two mills, one dedicated for raw mill grinding, the other one for cement grinding, or two. These are identical machines, and for sure, the classifiers are adapted to the material. It's a high fineness for cement. It's a low fineness for raw mill. The size of the TSV classifier is, generally speaking, bigger for raw mill, even if we have the same size of raw mills. And for sure, what is different in the operation of the raw mill is only the grinding pressure. Typically, the grinding pressure in the cylinders for cement is roughly in between 180 to 200 bar, and the same machine used in raw mill grinding, or an identical machine, operates in between 120, 140 bars. But these are identical machines, identical cylinders, identical sleeves, identical liners, and so on.
Okay. Kiran May just clarifies, he is actually talking about using one machine for both cement and raw grinding. I'm not quite sure how that would work. Do you have any examples of customers?
We have done it. We have done it in projects. We have never gone to actual execution because you have to be very careful when you size, because obviously you have to consider the time sharing for different capacities quite carefully in order to not to be too tight on the using time per day. So it theoretically can work, but generally we have a specific air circuit where we can switch from one type of classifier to another type. So high fineness for cement and low fineness or medium fineness for raw mix. So in our opinion, it would make sense only in a quite small plant. If you start to reach too high capacity, the collision between the using for cement and for raw mix become too critical. So it is feasible technically, but it would be only making sense for small plants.
Okay. Well, thank you very much for all of your answers, and thank you to